Okay, so finally seem to have all my computer issues working. So sorry about that. So what I'm going to do, I have a good bit of this left. I'm actually going to come back to here because it looked like somewhere around the middle of this problem. This one went pretty good, the 0, 5, and I'm going to start converting these 2 points from rectangular coordinates to polar coordinates because that's about where the video starts getting goofy. So converting to polar coordinates from rectangular coordinates, and I have the point -2√3, comma 2. And I want to turn this into polars. So there's a couple things I want to do. I always think the first thing I want to do is draw myself a little graph so I have some idea about what this thing's going to be. So -2√3, +2, I'm going to say it's over there somewhere. So what I need is my R and my theta. I know 2 things as far as formulas go. I know x squared plus y squared equals r squared. And I know theta is the inverse tangent of y over x. But this isn't really a straightforward formula. We have to be careful because if I did the inverse tangent, remember, that's only going to give us this side of the circle. My theta is specifically defined between pi over 2 and -pi over 2. So it's not going to give us this one. Okay, so what I always think is the best thing to do is look at this as a triangle on its own. Okay, where this one right here is 2√3. I mean, I guess -2√3, but really it's the length of a triangle. And this height right here is 2. So there's my R. And this one's not quite theta, but I'll call it something else. I'll call it phi. Remember, what I want is theta, but I'm going to use everything in this triangle. All right, so I suppose, right, just from the Pythagorean theorem, so that is 4 plus 4 times 3 is 12, which is 16. But remember, that's r squared was 16. So my r is actually going to be 4. Now, I'm not going to do, I guess, again, technically plus r minus 4. But you can see by the way I'm defining this, I'm going to be using the positive r. I could have gone this way and gone backwards, but I just feel like this is probably the more straightforward one. Okay, I can also see, looking at this triangle, the tangent of my phi, I'm calling it, is 2 over -2 well, again, I'm really going to think about it as positive. Right? And that's going to mean my phi is pi over 6. But okay, I didn't want phi, I actually wanted theta. So if I'm just going to remind myself, I'll draw me a bigger picture here. So I found the r was 4, and I found this angle right there to be pi over 6. Okay, the reference angle. Well, that means the one that I wanted, which was this one, must be 5 pi over 6. All I did was I took pi, which was 1, minus the pi over 6, which is that, and I got this. It's the supplement, same thing when I was doing the inverse sine. But anyway, that's where I'm going to get my polar coordinate. R theta is 4 5 pi over 6. All right. Maybe I'll just zoom out to get it. See, if I went straight and said theta was the inverse tangent of y over x, it would have given me this one down here. That's why I think it's you don't really want to think about this as a formula necessarily. You want to think about this as little triangles. Well, I mean, I guess that's just me. Other people might do it differently. But this is how I think about it. Okay, next one. Point -4, -4, right? And I'm going to want to turn that into polar coordinates. Well, whatever, you get the idea. Which is r theta. So I'm going to draw myself a picture so I know where I'm at. -4, -4 is there. Okay, so what I'm going to look at is this triangle that got made. I'm going to do it over here on the side. So my reference angle is this phi right here. Right, the theta that I want is this one, but this is what I'm going to find. And I'm going to think about this just as the point 4 and 4. So I can figure out the r. Just with the Pythagorean theorem. And so r is going to be the square root of 32, which is going to be 4 times the square root of 2. Okay, now for the theta. So maybe we can just see right here that we have the same two lengths, so we know it's going to be a pi over 4, but I can do this out right here. So I'm going to say the tangent of phi is 4 over 4, which is 1. And so I'm going to say phi is the inverse tangent of 1, which is pi over 4. So I only have to think about that first quadrant. But that's what phi is, right? So if I go back to my little shape right here, my little sketch, I know this is pi over 4. So the theta that I need which is 5 pi over 4. So there we go. The coordinate r theta is 4 root 2 5 pi over 4. And there goes our answer. Let me just zoom out. So you see, I like to think about these as like I'm solving an actual triangle with lengths, not really the -4 and the -4. That way I'll be able just to see you the little reference angle is and then just add or subtract as needed. Okay. So now we have the equations, right? So I have these equations in rectangular form with x and y, and I'm going to turn them into polar. And then I have some polar equations with r and theta that I want to turn into rectangular with x and y. Okay. Okay, so 5. First one is 5y squared equals 3x minus 2y. And I want to turn this into polar. Okay, so couple things. I guess really, if you go back to the beginning, remember, well, here, if you just think about a little triangle. That's r, y, x, and that's theta. Remember I said that the sine theta is y over r, and the cosine of theta is x over r. So if I wanted to solve for y and x, we have them right here in terms of x and y. Okay, so all I'm going to do is just sub everything in. So I've got 5 times r sine theta squared equals 3 times r cos theta minus 2 times r sine theta. And that's really about all we can do with this one. Nothing's really going to simplify. So there we go, I've done it. I just substituted y to be r sine theta and x to be r, oh, hell, why don't you want to stop me? Sorry about that. But I did it all right after that, right? So cool. X has become cosines, y becomes sines. All right. The next one we got is y equals x squared. So I'm just going to do the same thing. I have r sine theta equals r squared cos squared theta. So I guess if I wanted to solve this, I can kind of solve this thing for r because it's nice here, right? I guess I could divide both sides by r. And I'm going to kill those and one of those. And I'm going to be left with like that. Then I suppose I could divide off this cosine squared. Okay, if I flip it all around, okay, here's what I'm looking at. R equals sine theta over cosine squared theta. So if I'm going to simplify this a little bit, what I can do is I can pull one of these cosines out. Cosine squared means cosine times cosine. Because then I have tangent right there and secant right there. And I can write this as r equals the tangent of theta times the secant of theta. So if we can solve these things for r, we'd really like to do that. This one actually was kind of a goofy example because We didn't really bother too much with it because it's not going to get very nice. But this one is a nice identity, and so we might as well go ahead and solve it. You know, I guess I actually could have done it on this one. Maybe I should just finish it off. I'd do the same thing I did on that one. If I divide everything by r, what I get is 5r sine squared theta equals 3 cos theta minus 2 sine theta. Then I can divide everything by, to solve for r, to each term. Then I get what? R is 3/5 playing the same trick I played over here. And this one of my signs cancel. And now I have nice identities. Cosine over sine is cotangent. And this is probably a better fully simplified answer. Okay, let me draw a little line here and go back over what I did. Right, so after I did all these substitutions, I guess the first thing is I had an r common to everything. So I was able just to cancel that off. So I did that. Then I want to finish solving for r. So I divided everything off. Then I just took the 3/5 out front, cosine over sine, there it is. And then they had one more sine left, there it is. Then this one just reduced, 1 over sine, and then cotangent, cosecant, cosecant. All right. X equals 4. Well, this one's pretty straightforward, right? X is r cos theta, so I'm just going to do that. But we like to solve it for r, so I'm going to go ahead and divide both sides by cosine. And 1 over cosine is secant. And there we go. And one more, and I can just fit it right here because this one's actually really nice. You might remember this is a circle, right? Maybe just note. With radius 3. Well, I have, right? So if I have r squared equals 9, I guess that is r equals 3. Oh, okay, so no matter what theta is, you have a radius of 3 for all theta. Oh yeah, that's actually going to be exactly what a circle is, right? That is an awful looking circle, but you can get the idea, right? It's 3 all the way around for all theta. Cool, so I can turn rectangular equations into polar equations. Now, a lot of times there would be good reasons you'd want to graph such things. We're not going to have time to get into any of that. So I suppose for now, all we're really worried about is just abstractly turning rectangular equations into polar equations and vice versa. And all I'm using is these, I guess, three things. Well, okay, so to convert rectangular to polar, I am going to use x is r cos theta, y is r sine theta, and x squared plus y squared equals r squared. And then you can just convert everything from there. All right, so the last thing they have on this sheet is converting polar equations to rectangular equations. Okay. So I have r equals 2 cosecant theta, and I want to turn this to rectangular. All right, well, I guess what I'm going to notice here is I have cosecant is 1 over sine. Then if you multiply both sides by sine here, well, I guess what? That r sine theta, well, that is just y. So y equals 2. And I'm done. All right. Okay. This one's a little goofy. It's got a trick. So here's the two things I'm going to know. R cosine theta is x, right? So that would be handy. And if I had r squared, that would be x squared plus y squared. So what I'm going to do is I'm going to realize that, yeah, this was r squared, that would be good. And if that was r cosine theta, that would be good. So I'm going to multiply both sides of this by r. And that's a good little trick that you're probably going to want to keep in mind because it comes up. Because here, now I get r x squared plus y squared and r cos theta, that's x. So I got x squared plus y squared equals 6. So what is this thing? This is actually a circle. And maybe we're actually fine if you stop here. But for what it's worth, the equation for a circle, you might know from somewhere. So I can actually see that this is a circle. So I'm going to go ahead and solve it because so you can have seen it. I'm going to subtract 6x on both sides. You're going to notice I left a little bit of a space here. And that's because what I'm actually going to do is I'm going to complete the square on this. Which means I am going to add 9 to make this a perfect square. And I'm going to also add 9 over here, because now this thing factors into x minus 3 squared plus y squared equals 9. And I guess what's interesting about this, I suppose, is that I have, this is a circle at 3, 0 with a radius of 3. Oops. So I guess the reason that's interesting is I actually get an idea, oops. In the beginning, right, you see this, I was graphing r equals 6 cos theta. Circle centered at 3, 0 of radius 3. Right, so there's my point 3, 0. So if its radius is 3, it's going to go out to 6, 0 and back to 0, 0. And I'm going to do an awful job drawing the circle, but I'm going to try. Hey, that's not so bad. But look, what is this shape coming out between 0 and 6? As a polar equation, this is r equals 6 cosine theta. So actually, I would say I can look at this, and it's a much nicer looking thing than this, but certainly than this. But anyway, just to get an idea, the main point is, here was your answer when you did your little solution. And if I wanted to go further, I would go to here. Which one do I have next? Let me just zoom out a little bit so you can see the whole thing. All right. Okay, the next one they give us is much nicer. They give us r equals 7, which I guess I already know what that is, right? That's the circle with the radius 7, right? But what am I going to do? I want to have r. I don't really have a thing for r. What I have is that r squared is x squared plus y squared. So what I'm going to do is I'm going to use r squared equals 49. And then I'm just going to sub that right in there. X squared plus y squared equals 49. And there I go. Circle of radius 7, which we already knew. All right, then they give me what? Theta equals so before I go through and start actually doing this algebraically, what is this? What does this look like? So for all r, right, theta is a constant 3 pi over 4. So if I was going to draw that, you're going to put your theta at 3 pi over 4, which I guess is over here, right? And it's going to continue infinitely out in that direction. For those are all the positive r's, and back here for all the negative r's. all positive r's, and this is all negative r's. So this is going to be a line through the origin. So when it comes to polar equations, constant r's are circles, constant thetas all lines through the origin. Okay, well, how do I do this? I said this is how to think about it, but how do I solve this algebraically? The thing we're going to use is that the tangent of theta equals y over x. Okay, so I guess I'm going to take the tangent of both sides. Okay, and tangent theta is y over x, and tangent 3 pi over 4 is -1. So, right, I can just solve that thing for y. Y equals -x. And yeah, like we thought, line through the origin. Intercept 0, slope -1. All right, so again, with the thetas, you're using the tangent theta as y over x. And otherwise, I'm using that x is r cos theta and y is r sine theta. Okay, the next one it gives me is r cos theta equals 6. Well, that's easy. That's just x, isn't it? And I guess done. Okay. Next one I got is r sine, I'm sorry. R equals 4 sine theta. So this one is the same kind of deal as this one, right? Instead of having r cosine theta, I have r sine theta. So I'm going to play that same trick. See, why I want to make sure I'm pointing that out. This trick is the thing you're going to want to do. So just like before, multiply both sides by r. So I've got r squared equals 4 r sine theta. R squared is x squared plus y squared. And r sine theta is y. Again, we're pretty happy here, but I'm going to play that same thing I played before. Well, I'm going to subtract the 4y from both sides. I'm going to leave myself a space. So I need half of 4, which is 2 squared, which is going to be 4. And I'm going to add it to both sides. So that is y minus 2 squared equals 4. And what I got a circle with center 0, 2, and radius 2. Remember, the square root of 4, right? That looks like it's 2 over the square root of 4. Okay, so on a graph, what? I'm centered here. I'm going up to radius 2, so 4 and 4. And you're going to look like that. So see, our for sine theta, look, you got a circle that's facing upwards, like the y, like the sine, and it goes out to 4, right, from 0 to 4. And when it was cosine, it went this way, right, towards the axis, right, towards the x-axis in the horizontal direction. That's the word I'm looking for, in the horizontal direction. X is like cosine, y is like sine, and still it had that distance of 6. I guess what's the word? Diameter. Diameter of 6. Again, not that we're worried too much about graphing these things at this point in time, but just to give you an idea of about where this is going. All right, one last one. Well, I've got 1 over sine theta minus cosine theta. All right, so I guess what I'm going to do is I don't like it there on the denominator, so I'm going to multiply both sides of the equation by that. So I kill them all there. And then I get r times sine theta minus cosine theta equals 1. Then if I distribute my r, r sine theta, that's y. R cosine theta, that's x. Which is a nice line, not through the origin, but through that point, 0, 1. Okay. So, sorry that took so long, but it's all out there now. And I'll remind you in the email, but this 9.1 homework is going to be due Monday for my math lab. On that, I guess I'm going to get back to grading. You guys have a good weekend.